Terminal voltage lab says make the circuit at the left, which I did. There's two batteries going in the same direction. There's wires, a switch, bulb 1, bulb 2. Let me move this over. It's a little easier to see possibly. Okay, so it says open and close this. So first of all, let's make, there's bulb 1. Okay, now let me close the switch. Now I'm going to put my hand over this so you can see what's happening with bulb 1. It is dimmer, brighter, dimmer. Now it should make sense to you that this one comes on and off. No big issue. There was an open circuit, now there's a closed circuit. But what's going on there? Let's continue. What did you observe? Bulb 2 came on. Bulb 1 got dimmer. Since they're in parallel, they must have the same voltage. So supposedly these have the same voltage, but this resistance didn't change. And if it gets dimmer, for it to change brightness, it must have less current. And the only way, if it's the same resistance, to have less current, if there's less voltage. Somehow the voltage changed there. But let's make this more obvious. Now this next part of the circuit, let me show you how I've got this hooked up. This is an ammeter. Let me remove this. Notice it's COM and 10 amps. So for this one, I'm going to want 10 amps, which is over here. And I want this one in 10 amps. And this is the darkest one I found there, so that's COM. Okay? I put those here. And I move, that's 10 amps here, COM, and voltage. And I'm going to put that to 20 volts. Hook it up here, top part of the battery, bottom side of the battery. All right. Now notice right now what it's reading, 2.82 volts. And now I'm going to move this to current, 10 amps. And then it says, make the circuit at the left, use 10 amps, etc. Because again, if you use 200 milliamps as possible, it would be too much for this multimeter. 20 volts and the ammeter to 10 amps, so I need to fix that. With a switch open, measure the voltage. The voltage is 2.82. Turn the variable resistor to its maximum value, which I think to be there. Let's find out. And then I close switch. There we go. Notice it dropped just a little bit, and we do have some amperage. Now I'm going to make the current should go up eventually. And notice as the current goes up, the voltage goes down. Now the voltage has gone down a lot. Current goes down, voltage goes up. Voltage goes down as the current goes up. Okay, and then with a break, it reads the maximum of the batteries. Now let's do the analysis. All right, let's talk a little bit about what just happened there in the lab. You'll notice on the questions that it has there, it says, while looking closely, etc., what happened? We noticed that when we had more current, we had less voltage. Now, why would that make any sense whatsoever? I'm sorry, I'm trying to keep this thing from sliding down. I don't have a tripod or anything. Now, if we were to take this little battery here, okay, it's a 1.5 volt battery, and if I were to put 0 resistance across it, according to Ohm's law, V equals I times R, it should put out an infinite amount of current. Now, a vacuum cleaner at the house puts out about 12, it needs about 12 amps in order to work, okay? I don't think that you could put this into your vacuum cleaner and get it to power it. It just doesn't have enough chemicals, etc., okay? So it turns out that a battery, due to its configuration, due to the physical configurations and the chemicals, etc., has a limit to how much current you can push out. This is where terminal voltage comes into play. When you just have the metals and the chemical reaction, you get a theoretical maximum. This right here is 1.5 volts if everything's going right. But as I start to ask it to give more and more and more current, it just can't keep up because there's a limit to the chemical reactions. I know in chemistry they do, chemical limiters and so forth, how fast a reaction can go. Now, a bigger battery, like again, you take this versus a AAA battery. A AAA battery can't put out as much current as this can. That's why you use D cells in the old-fashioned light bulbs, which use a lot of current. And why a car battery, which is of course more voltage, can put out 600 or 700 amps of current, because a car battery has giant plates on it, and so all this chemical reaction can go very, very easily. Okay, so that's really what it comes down to, is that you're asking all of these electrons to move at one time between the different plates of the metals with the chemical between them and so forth, between the cathode and the diode, or in the the anode and the cathode. But it just can't do it. And so as a result, a battery has what we call an internal resistor. Now, it's not an actual resistor like, a resistor, but it's a limit to how much current can flow out of that battery. Now, you'll notice, let me go ahead and pull up the diagram I have here. Actually, I can just flip it. Maybe I can't. Here's the diagram I want you to memorize. So we have R of anything that's connected to the circuit here. And then we have the battery, there's the copper top or the pointy end, and you have the EMF. That's your theoretical. That's what you think it can do. And then over here, you've got this little bitty resistor inside. We use a small r to signify an internal resistor, okay? And here's our equation. We have VT, our terminal voltage, that's across the top of the battery, equals your EMF minus IR. EMF minus IR. This is just like in a series circuit where you have a battery, and then all of a sudden you go across a resistor and the voltage drops. So just because there's current running through that little R, there's going to be a voltage drop across it, and VT will be smaller. So as I gets bigger, VT gets smaller, but EMF will stay the same. Now, what about this internal resistance? It actually turns out it will change over time. As the battery gets old, then that little R goes up until it just can't run anymore. And you try to ask any kind of current at all come out of the battery and it won't flow. This is why a battery tester, you have to have a battery tester that doesn't just read voltage. At your house, if your battery in your car is not working well, you might go out with a voltmeter and read it and it says, oh, you've got 12 volts. And then you can't run your car. Well, the reason is that when you're not using it, I is 0, and it's still reading 12 volts because there's still the same metals between them, etc. But little r has gone up so big. Why? Because the different parts of the battery are wearing out. It's given all the electricity it can, and now there's no receptors or no chemicals able to send out that current. Now let's look at the other side over here. Big I, big R. Big R would be the rest of the connected circuit, whatever it is. You connect something to the battery, a light bulb, whatever it is. But this is internal to the battery, okay? Now, interestingly enough, with using these, you can actually calculate the maximum current from a battery. So if you go over here and you were to make this equal to 0, you might say, oh, well, infinite current. You still have this little one. You make this equal to 0, then EMF divided by little r will tell you the maximum current for that battery. Okay, now usually I do this with a rechargeable battery because I have those in my lab, but with the whole coronavirus thing there at home. So I'm going to connect these leads from this power this power eliminator so that I can use this instead of, because this will go higher voltage. Okay, then I'm going to take my leads here and let's put this on 20 volts, and let's see what the voltage is across this battery. Okay, right now the voltage is 1.36 volts roughly. Now I have to push harder. I'm going to put 2.2 volts. You might think, oh, it's going to read 2.2 volts. That's obvious. Let's find out. It reads 1.8 volts, 1.83 volts. I turn it off. It reads 1.4 volts, a little higher. Once again, when I push into it, it reads 1.82 volts or something. Okay, which tells us that when a battery is being charged, the terminal voltage is higher than the terminal voltage is higher than the EMF. Let's go ahead and show why it is that a charging battery has a greater terminal voltage than EMF. So if you'll notice here, I have the current leaving the battery. This is normal operation discharging. It's going to a light bulb, it's going to whatever part of the circuit. Let's say that the EMF is 12 volts and we have a 1 ohm internal resistor, and let's say it's putting out 2 amps. Well, EMF minus IR equals the terminal voltage that you read at the edges of the battery. Well, we have 12 volts minus 2 times 1. That's the taking away by the internal resistor. But you only read 10 volts outside the battery. But what if it was charging? Now the current's going the opposite direction. We'll call it again 2 amps. We'll keep everything the same except the direction of the current. Well, now EMF minus IR equals VT. You have 12 minus a negative current. It's going the opposite direction. And that now gives you 14 volts. It now reads higher than the EMF because you're pushing against those chemical receptors, trying to squeeze those electrons back into their position. Let's use another analogy here to see if this helps you make sense of this. We have an object on a ramp. Let's say that this is 100 joules. We'll make this easy. Potential energy at the top. Let's say it loses 10 joules of friction as it comes down the ramp. And so at the bottom, it would only have 90 joules of kinetic energy because it lost some in the transfer. It's not completely efficient. But what if it was going upwards? It's going the opposite direction. So it gains 100 joules of energy at the top, but it's going to lose that 10 joules going up against friction. So here it has to have 110 joules of kinetic energy to get up the ramp. Now let's connect the analogy to the battery. This right here, your potential, your maximum potential that you have is your EMF. This is obviously, the friction is IR. And then what you actually get out, what you see outside the ramp would be your terminal voltage. This would be this would be discharging. Normal operation. This would be charging. With a discharging battery, normal usage, your EMF is greater than your terminal voltage. For a charging battery, the terminal voltage is greater than the EMF because of the inefficiency of the battery. It cannot put the electrons back into its chemical receptors fast enough. Okay, now we have a car battery. I had to get a neighbor to help me out here because I have a hybrid and it's all messed up. Okay, so I'm going to put this to 20 volts. And notice, with everything off, it reads 12.5 roughly volts. Now let's turn on the lights. And notice it dropped. So it's discharging and the battery, because it's putting out current, now the terminal voltage has dropped. Now, okay, turn off the lights. Goes back up to the EMF. That's what the battery reads when there's nothing being done. Now watch what happens when we turn on the car, so that's charging the battery. $14, that's perfect. So now, because the current's going the opposite direction through the battery, the IR is now, I is negative, so IR is now a positive IR, and it's greater than the EMF. Thanks, Bob. Appreciate it.